joined yet, so let them join the class by that time. Okay, please wait.
Okay, ma'am.
I'm going to start the recording. Good morning, students.
Good
Good
morning,
morning.
ma'am.
Good morning, ma'am.
Please be ready with your notebook and calculator. Today we'll solve numerical problems from Module 3 Transformer. Let us first start with short circuit and open circuit test of transformer. Please wait, I'll be sharing my screen. Is the screen visible to all of you?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So let me explain open circuit test and short circuit test briefly before going to the numerical part. These two tests are very, very important tests in transformer, but these two tests are not included in your theory syllabus. Why we perform these two tests? Probably you have performed these two tests virtually in your basic electrical laboratory class. What is open circuit test? Why we perform open circuit test? What is the requirement of this test in transformer? See, I have told you that in transformer operation, we need to estimate the amount of core loss and copper loss. These two are major losses found in transformer. Core loss, mainly the iron loss, which is comprising of two losses. One is called the hysteresis loss and second one is the eddy current loss. And copper loss is mostly the ohmic loss or the I squared loss, mostly found in the transformer windings, right? Ideally, we assume these losses to be equal to zero because we ignore the leakage flux, the concept of leakage flux and its effect in the transformer windings. But in practice, no transformer is ideal. So definitely these losses are unavoidable. So we need to measure these losses, right? Now, mainly open circuit test is used to measure the core loss, the iron loss, that is the hysteresis loss and eddy current loss. And short circuit test is mainly used to measure the copper loss or the ohmic loss. Okay, so look at the circuit diagram. This is the circuit to be formed during the open circuit test operation. See, always the high voltage side is left to be open. You can see this is the high voltage side of the transformer, and all the instruments or the measuring devices, the meters are connected with the low voltage side, or you can say that low voltage side is actually connected with the single phase AC mains supply. So what we'll do, we'll first connect the single phase mains, the AC supply, that is 220 volt 50 hertz AC supply, connected across a variac, which is an auto transformer. It is required to vary the supply AC voltage only. Across a variac, a voltmeter will be connected to measure the supply voltage. These two are fuses. So the supply mains will be connected now in series with an ammeter to measure the supply current and one wattmeter in series with the primary winding of the transformer. So if it is a 220 by 110 volt transformer, 220 by 110 volt transformer, that means 220 volt side will be left open and 110 volt, that is the low voltage side, will be connected with this input side or the input voltage of the transformer. And this is the wattmeter, you know the symbol of wattmeter, MLCV. These are four major terminals of wattmeter. Fine. M means mains, the terminal which will be connected with the main supply. L means load. That means the load side will be connected. Here it is the primary winding or the low voltage side winding. Fine. And these two are coils present in the wattmeter, current coil and pressure coil. Current coil, that the coil which is having lesser number of turns connected in series with the supply mains will be carrying only the supply current. That's why one ammeter is placed in series with this current coil to measure the series current or the supply current. And pressure coil will be having more number of turns because it will be carrying pressure, the voltage of the circuit, and that will be connected in parallel of the main supply. See here, this pressure coil is actually connected in parallel with the variac or in parallel with the voltmeter to measure the voltage of the circuit, right? And obviously this is a unity power factor. It should be a unity power factor wattmeter, mostly the electrodynamometer type wattmeter, right? Where we measure power by multiplying only the voltage reading and the current reading, assuming the power factor as unity, because power, the true power is actually VI cos phi. So wattmeter reading, the RMS value of the power, the wattage value will be just the product of RMS voltage and RMS current, right? You can also multiply these two values also, right, to get the power. But in that case, you need to measure, you need to calculate the power factor of the circuit also. But this wattmeter, since it's an electrodynamometer type wattmeter or unity power factor based wattmeter, if you connect this wattmeter with the circuit, you will be able to measure the power directly from the reading of that wattmeter. But always remember, in transformer operation during the open circuit test, we do not require any unity power factor based wattmeter. We do not require unity power factor wattmeter because during the open circuit test operation, the power factor of the circuit is very, very low. The power factor of the circuit is actually very, very small. That's why we do not require unity power factor wattmeter here in this case during the open circuit test. We require mainly the low power factor wattmeter, mainly in the range of 0.2 to 0.3. Very low power factor wattmeter we require during this test operation. Fine. So what we'll do, you will measure the input voltage, input current, input power from the three instruments connected with the input side, with the low voltage side of the transformer. Okay, and the high voltage side will be left open. Why? Why it is so? Why will connect low voltage side with the single phase transformer? Because open circuit test means the high voltage side is left open, right? You can see there is no load connected here. This is the secondary winding. So secondary winding is not connected with any load. That means it's just like a no load operation of transformer. It is just like a no load operation of a transformer, right? And during no load operation, as I told you earlier, the no load current is only required. No load current or the exciting current is the only input current to be drawn from this supply voltage in order to magnetize the core only, because no such other operations are going on because the secondary circuit is totally open. So only a small portion of current, mainly 2 to 5% of the rated current, which is quite very small amount. This small valued current is only required to be drawn from the input supply voltage in order to magnetize the core. Already you have learned why the core needs to be magnetized always, right? To uh, satisfy the transformer operation smoothly, we need to confine constant flux within the core, right? Flux should not be varied within the core material. It should be kept constant, right? Otherwise, there will be a chance of reduction of primary as well as secondary induced EMF across the two windings, primary and secondary windings respectively, which in turn will affect the actual working of the transformer. Okay. Now, if we connect the low voltage side with the input side, what will happen? Very low current will be uh, drawn, right? Very small current will be flowing through the windings. It's a practical transformer, so definitely leakage fluxes are there, right? So leakage flux will create the effect of magnetizing reactance as well as the loss component of current supplying the core loss, etc. in the transformer operation, right? That means there is a concept of R1 X1, the primary resistance, primary reactance in the equivalent circuit. If we draw the equivalent circuit, you will see this is the equivalent circuit. This is the equivalent circuit. Is it visible?
Yes, ma'am.
Already I have explained this equivalent circuit. See, the equivalent circuit is only having the input parameters like the low voltage side parameters. This is the primary winding resistance, primary winding reactance, and this is the no load components, right? No load current I naught, because now secondary side is left open. There is nothing at the secondary side. Okay. So primary current will be only drawn from the primary voltage in order to magnetize the core. And these effect will be represented by these two parameters in the equivalent circuit, the Xm magnetizing reactance and RCL, the resistance supplying the core loss only. So no load current will be divided into two parts, and that will be reflected in the phasor diagram in this way, that Im, the magnetizing current, will be in phase with the main flux, which is the reference vector here, main flux or the mutual flux, and ICL is the current supplying the core loss, which will be perpendicular with the magnetizing current, and the resultant is the no load current, I naught. So this is the primary current, only primary current, which is required to magnetize the core, because the secondary side is not connected to anything. Okay. Now, ideally, this no load current vector should be in phase with magnetizing current, but in practice, due to the concept of leakage flux, this current will be making an angle theta 0. And see this angle. This is called the power factor angle. Why it's called power factor angle? Because we know power factor angle is the angle between the input voltage and in the input current. Right? Here, what is the input voltage during the no load operation, during the open circuit test? Input current is I naught, and what is the input voltage? It is V naught. It is V naught. Look at the equivalent circuit. This is the input voltage. This is the input current. So angle between these two quantity is known as power factor angle. And cosine of this theta 0 is called the power factor. This is called the power factor of the circuit during the no load operation. Okay. Now, as I said earlier, that this vector I naught should be in phase with Im as much as possible in order to ignore the losses, right? This component ICL must be very, very small compared to Im, right? And this ICL is the current supplying the core loss, right? So in order to reduce the core loss, this vector should be near to the vector Im. That means this angle should be very, very small. And this is 90. This is 90 degree. That means this theta 0 is 90 minus this angle. Right? So if this angle is very small, then definitely this angle will become 90. This angle will become 90. But now it is theta 0, which is quite a large amount. Right? If you assume this angle is small, the 90 minus theta is very large. Right? And cosine of that theta will be very, very small. That is actually the power factor. That means during this open circuit operation, open circuit test operation, during this no load operation of transformer, the power factor, the input power factor is very, very small. That's why we need very low power factor type wattmeter, LPF type wattmeter. Okay. Is it clear to everyone? And next,
Yes, ma'am.
what we'll do, next we'll measure the no load power factor cos theta 0 using this relationship W naught by V naught I naught. V naught I naught will be measured by the voltmeter ammeter connected with the circuit, with the low voltage circuit, and this W naught is the wattmeter reading. Okay. Now from the phasor diagram, Im can be calculated as I naught sine theta 0. From this you will be able to calculate theta 0 and then sine of theta 0. So magnetizing current can be calculated using this relationship. Similarly, core loss component of current ICL can be calculated as I naught cos of theta 0. This can be also obtained from the phasor diagram. So finally, magnetizing reactance Xm across the low voltage winding is just V naught by Im. Look at the equivalent circuit. It's just V naught by Im because current flowing through this Xm is Im. And what is RCL? It is just V naught by ICL. V naught by ICL. Fine. That means by using this open circuit test, we'll be able to calculate these parameters: the no load power factor, then the magnetizing current Im, loss component of current ICL, magnetizing reactance Xm, and the resistance representing core loss RCL. Okay. That means during this test, during this open circuit test, the input current is very, very small, which is called as no load current, mainly 2 to 5% of the rated current. So the winding, these winding resistance and reactance will draw very, very small current, right? Say this current is I, which is very, very small. Fine. That means I square loss, I square R, the ohmic loss is also very, very small. This is actually the copper loss, mainly denoted by P copper, right? That means copper loss is very, very small. So we can ignore copper loss during the open circuit test operation, right? Actually, this wattmeter is measuring both the losses, both the core loss and copper loss, right? Okay, but copper loss is very, very small here. Why? Because the current is very small. The input current drawn by this primary winding resistance and reactance is very, very small. So square of that current is also very small. So I square are very small quantity. So we can neglect the copper loss. So the only component of power to be calculated from this wattmeter is the core loss. That's why we'll arrange the circuit configuration in such a way that low voltage side will be connected with the input side and high voltage side will be left open, because we want to measure only the core loss by this test. So open circuit test is only used to measure the core loss along with this input side parameters IM, ICL, XM, RCL. Okay. Now you can draw the equivalent circuit, refer to primary, refer to secondary. You know how to calculate the quantities like XM, RCL when referred to the secondary. When referred to secondary, it will be divided by the square of turns ratio. If it is referred to primary side, then it will be multiplied with the square of turns ratio. Okay. And what is the short circuit test? See, it is just reversed in case of a short circuit test. As per the equivalent circuit is concerned, now this time low voltage side will be left shorted. And all the instruments devices will be connected with the high voltage side, because now this time using short circuit test, we actually want to measure only the copper loss. Only the copper loss, right? So what we want to do here, we want to connect the high voltage side with the supply side, with the main supply voltage, so that rated current flow uh, through the windings. We'll connect the rated voltage here across the high voltage side, across the primary winding. This time primary winding is actually the high voltage winding, right? So what happens actually, if we connect the rated voltage or rated current, only the rated flux will be flown through the core material. And when only rated flux is confined within the core, what will happen? There will be very, very small core loss. The core loss will become very, very small, right? So only loss at this situation will be measured by using this wattmeter, that is the copper loss. That is the copper loss, because only the rated current will be flowing through the windings. The secondary side reactance and resistance, because this time the secondary side is connected. It's not open, it's connected via short circuited wire, right? So secondary current or the short circuit current will be flowing through the circuit. Fine. So we'll only able to measure the copper loss, or sometimes it is known as short circuit loss, because this voltmeter will measure VSC, this ammeter will measure ISC, so this wattmeter will measure WSC, right? Because this time, since we are supplying rated voltage as the supply voltage to the high voltage side winding, what will happen? Very, very small current will be flown as the short circuit current, which is very, very small, typically about 5%, right? Since the rated current or the rated voltage is supplied here in the primary side windings, the high voltage side windings are basically energized, excited by very, very, I mean, rated current or the full load current during this short circuit test operation. Okay, so that small amount of short circuit current can be flown, right? So this time the flux level will be very, very small because the current is very small. Okay. See, if it is a rated voltage at this side, at the input side, what will happen? In order to maintain the EMF equation of the transformer, we all know it is V1 I1 equals to V2 I2, right? So if V1 is high, definitely I1 should be low, right? That means small current is flowing through the core. Very small current is required. Very small amount of flux is required to be confined within the core in order to satisfy the transformer operation. That means core loss is negligible. It is small, right? So that's why we can ignore, we can neglect the core loss here. Only loss we can measure, that is the copper loss, by using the wattmeter. So here the parameters are given from the short circuit test operation of a transformer, that equivalent resistance is wattage by square of current, referred to the high voltage side, obviously. This is the equivalent impedance, that is voltage by current. This is the leakage reactance, that is square root of impedance square minus resistance square. These three parameters can be calculated. And WSC is just the wattmeter reading, that is the only copper loss, right? And if you divide this loss, the wattage, by square of current, you will get the equivalent resistance. Equivalent impedance can be calculated as simply V by I, and you know impedance square is equals to square resistance square plus reactance square. So reactance, equivalent leakage reactance, can be calculated as under root square of Z minus square of resistance, right? Now with these parameters, again you can calculate equivalent resistance and equivalent reactance of low voltage side winding by multiplying these parameters REXC by A square, where A is the turns ratio, number of turns at the low voltage side winding divided by number of turns at the high voltage side winding, keeping in mind that here high voltage side will be connected with the metering side. Is it clear to everyone? Why it is required to perform open circuit and short circuit test, and what are these two tests? The circuit configurations, equivalent circuit, and phasor diagrams. Do you have any queries, any confusions up to this? No confusions, right?
No, ma'am.
Okay. Please note down a problem. Can you see my screen? Please
Yes.
Yes, ma'am.
circuit diagram. Draw this circuit diagram. This is the open circuit equivalent circuit, and the phasor diagram. Here supply voltage is 200, supply current is 1.25 ampere. That is the no load current. And high voltage side is left open for this test, right? So definitely RE1 and XE1 are the input circuit parameters, input circuit impedance. IM1 is the magnetizing component of current. ICL1 is the core loss, current supplying the core loss. How to calculate the no load power factor cosine theta 0? Here the entire power is 150 watt to be dissipated in this resistor RCL1, that means through this resistor. That means this is the power measured by the wattmeter connected in series with this winding with this low voltage side. So 150 watt divided by what? V0 and I0. This is V0, the input voltage. This is the input current I0. So power factor, the no load power factor cosine theta 0 is W0, the input power, divided by V0 I0. Okay, so from this we can calculate theta as well as sine of theta. So then we can calculate IM1, because I01 is 1.25 multiplied by sine theta, so it's 1 ampere, and core loss component current ICL1 is I01 of cosine theta 0, so it's 0.75 ampere. Okay, because the value of no load current is given in the problem. No load current is 1.25 ampere. This current, this is the no load current. So this is IM1, the magnetizing current, this one, which is I01 into cosine theta 0, and this current ICL1 is I01 into sine of theta 0. I hope all of you have understood up to this. And finally, the magnetizing reactance XM1, that is V1 by IM1, V1 or V0, whatever you say. So it's 200 by 1, that is 200 ohm. And the resistance component supplying the core loss RCL1 is V1 by ICL1, that is 200 by this current 0.75. Here that is now RCL equals to 266.67 ohm. Is it clear to everyone?
Yes, ma'am.
Okay. Similarly, how to compute the short circuit test results? So this is the equivalent circuit diagram and the phasor, right? So this time the short circuit current is 12.5 ampere. So if you connect a wattmeter, you'll be able to calculate the power drawn by the circuit, that is WSC, or you can calculate it by multiplying RE2, the circuit resistance, with the square of the short circuit current, I square is C, right? So it's now 175.12.5 square. WSC is given in the problem as 175. This is 175 watt is just the copper loss. 175 is just the copper loss. That will be given in the problem. Okay. And ISC is given 12.5. So it's now 1.12 ohm. And similarly, impedance VSC by ISC, it is 20 by 12.5, 20 by 12.5 VSC. This data will be given in the problem. So VSC by ISC, that is ZSC, is 1.6 ohm, and it is equal to square root of resistance square plus reactance square. So XC2 can be calculated by using this formula, which is equals to 1.14 ohm. Okay. Next, coming to the second problem. Consider a single phase 5 kilovolt ampere 200 by 400 volt 50 hertz transformer. The equivalent circuit is shown here. Calculate, number one, the efficiency of the transformer at 75% loading with power factor of 0.7. Number two, at what load or kVA the transformer is to be operated for maximum efficiency. We haven't learned it yet, so we'll now skip it. Okay. Next, the regulation of the transformer at full load, 0.8 power factor lag. And last one, what should be the applied voltage to the low voltage side when the transformer delivers rated current at 0.7 power factor lagging at a terminal voltage of 400 volt. This is the problem. Look at the rating of the transformer. It's a single phase 5 kVA 200 volt by 400 volt 50 hertz transformer. Okay, and this is the equivalent circuit. You have to find out. Okay, also skip this part. You haven't learned efficiency yet. So find out the regulation of the transformer at full load 0.8 power factor lag and calculate the value of applied voltage to the low voltage side when the transformer delivers rated current at 0.7 power factor lagging at a terminal voltage of 400 volt. So this is the known data, that is the full load kVA rating, 5 kilovolt ampere. Core loss is 150 watt. Full load copper loss 175 watt. These two will be given. These two are known actually, the core loss and copper loss value. Voltage regulation. This is the formula of voltage regulation that you have studied in the last class. Per unit regulation R. It's I2 Re2 cos theta plus I2 Xe2 sin theta by V20. Can you remember this expression? What is V20? It is the no load voltage. Okay. I2 the secondary current is 12.5, Re2 1.12, Xe2 1.14. These two are given in the equivalent circuit drawing. Right? So it's just 4.9%. Calculate it. It is 4.9%. Okay. And
Ma'am, I2 is not given.
I2 will be given. I2 is not given here, I know. I2 will be given. Actually, they have taken the data from the last problem. I2 will be given. Or if it is not given, you have to calculate it. This will be the known data. The secondary current or the load current. Next, the last part of the problem to calculate the applied voltage when the transformer delivers rated current at 0.7 power factor lagging at a terminal voltage of 400 volt. So this is the numerator of the voltage regulation, that is the difference between no load voltage and the full load voltage, right? That I2 Re2 cos theta plus I2 Xe2 sin theta, that is the numerator, this part of voltage regulation. Right, where the terminal voltage is given as 400 volt V2. So V1 dash, that is the applied voltage to the low voltage side, calculated in terms of high voltage side, is 419.92. Right, this is the value. So it will be calculated from this expression, from the expression of numerator of per unit voltage regulation. So V1 is calculated as 419.92, right? Now this is V1 dashed. Actually, I have taken V1 dashed, refer to the high voltage side. Now the actual magnitude of this applied voltage across the primary winding is just A times V1 dashed. The primary voltage is A times V1 dashed. So turns ratio will be again given. It is 0.5. So V1 is actually 210. Is it clear now?
Yes, ma'am.
It was a 200
And
by
while solving, we have to show this write up also.
write up means?
Ma'am, this to calculate and then all.
Yes, yes. That means this you're
Yeah,
talking
this part.
this. Yes, yes, definitely. Otherwise, you can't explain why you are doing so. If you write only the formula, no one will understand what you have taken, because in transformer, always you have to draw the main circuit or the equivalent circuit as well as the phasor diagram. You have to mention whether you are taking the circuit, equivalent circuit, refer to the primary side or refer to the secondary side, because phasor diagram will be changed, right? If you consider the low voltage side, the phasor diagram will be something different if you take the equivalent circuit, refer to the high voltage side. So depending upon the type of phasor diagram, the calculations or the procedures of solving the numerical will be changed. The final answer will be the same, but the method will be changed. So if you just write down the equations, no one will understand that what is the actual method you are taking. Okay. Now, let me show you the problems given in the PPT. I think you have already studied the numerical problems given in the PPT, the first part of transformer. This is the first one. First problem that I have given. It's a 25 kVA, 25 kVA, 7200 hyphen 240 by 120 center tap single phase transformer operates at rated voltage. What is the meaning of this line? 7200 volt is the primary voltage, and secondary voltage is actually 240 by 120. It's a center tap. See, the rating of the secondary voltage is 240 volt, the total voltage across the secondary winding, but it's a center tap secondary winding. So centrally, I mean, with respect to the center point, the secondary voltage across the windings, across the two windings, will be 120 volt each. And impedance is 7.2 angle 36.9 degree. Assuming ideal transformer, you have to find out turns ratio, secondary current, primary current, load impedance as seen from the primary side, and PTST, QT, and FP. Ideal transformer means V1 N1 equals to, I think I should say V1 by V2 equals to N1 by N2. V1 by V2 is equals to N1 by N2. V1 means the input voltage, the primary voltage, right? So VP, which is 7,200. V2, the secondary voltage, VS, 240 volt. So VP by VS is equals to NP by NS, right? So that is 30. So for ideal transformer, turns ratio is 30. So secondary current can be calculated as A times IP, because IP by IS, primary current by secondary current, is equals to 1 by A. What type of transformer it is? Step down or step up?
Step down.
Step down from type transformer, right? So IP by IS equals to 1 by A. So IS, the secondary current, is simply A times IP. A is already calculated. Okay. Once secondary current is known, you can calculate primary current using the relationship 1 by A IS. And then the input impedance as seen from the primary side. Input impedance referred to primary side. As seen from the primary side means referred to primary side. So referred to primary side means always the impedance multiplied by the square of the turns ratio. So it's 6480 angle 36.9 degree. And hence all the secondary side quantities like apparent power S, product of VS and IS, using the primary side quantities apparent power VP into IP. See, both the powers are equal. That means the level of power is not changing. The primary power is exactly equal to the secondary power in any type of transformer operation, whether it's a step up or step down. Only the voltage or current level will be changed. Expressions of active and reactive power, PT, the active power, QT, the reactive power. Okay, and finally, the power factor. Power factor, if you can remember the power triangle, you will see that power factor cosine theta 0 is actually what? Active power, reactive power, apparent power. So cosine theta is actually equals to P by S. P by S. Active power by apparent power. Right? So it's 0.8 lagging. So similarly, you can solve this problem. It's a 300 kVA, 2400 120 volt, 60 hertz single phase transformer. Operates at 2300 volts on the primary side. See, this is the rating 2400 by 120, but the primary winding is operated at 2300. It supplies 115 kilovolt ampere to a load that has a power factor of 0.723 lagging. Assuming ideal transformer, find out secondary voltage at the operating primary voltage, secondary current, impedance as seen from the secondary, impedance as seen from the primary. Okay, so turns ratio here will be the primary voltage by secondary voltage. So it's 20. Okay, and secondary voltage is now the primary voltage by the turns ratio. Now this time primary voltage will be taken as 2300 because the transformer is operating at 2300 volt across the primary winding. But while you are calculating the turns ratio, always we need to consider the rated primary by the rated secondary. Similarly, you can calculate the secondary current. And next, the impedance as seen from the secondary side, Vs by Is. This is the load impedance of the secondary side. The secondary voltage divided by secondary current. That is the load impedance of the secondary. And next, the load impedance referred to the primary side. We'll just multiply it with square of turns ratio. S square into Zs. So we'll multiply the secondary impedance Zs, that is 0.115 angle 43.7 by the square of the turns ratio. Okay, is it clear to you? So try to solve more problems like this, more similar problems. So next day, the next tutorial class, again we'll solve additional numerical problems from transformer. Do you have any queries?
No, ma'am.
Roll number 1,
Present, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4,
Present, ma'am.
5,
Present, ma'am.
6, 7,
Present, ma'am.
8,
Ma'am, I'm roll number 6
Present.
and I'm present.
9,
Present, ma'am.
10,
Present, ma'am.
11, 12,
Present, ma'am.
13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Yes, ma'am.
17,
Yes, ma'am.
18,
Present, please, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Yes, ma'am.
24,
Present, ma'am.
25,
Present, ma'am.
26, 27,
Present, ma'am.
Present, ma'am.
28,
Present, ma'am.
29,
Yes, ma'am.
30,
Present.